Start the recording. I want to say a few things about these chapters that you've been reading in this online text about the history of Mars exploration. Only if one of you are in the class is officially declared as a history major, and so most of you probably don't care much about history. But clearly the history in any area of science is important for understanding how we got to where we are today. What I plan to do is just pull out some of the questions from today's quiz to talk about, and then try to give you a more comprehensible framework for thinking about these historical events, rather than just having one long list of who did what and so forth. And in 1857 this happened and blah blah blah. So we'll try to do that. Okay. So I just wanted to pull out a few questions about telescopes, because this era of Mars exploration, telescopes obviously were key. And I don't know how many of you have actually played around with telescopes or know the difference between a Newtonian versus a refractor telescope. But this is a question that a number of you had difficulty with. The question was all about how this development of this twofold lens system allowed refractor telescopes to make a comeback. There are two basic kinds of telescopes when we're talking about light telescope. One uses lenses to focus light. So it collects a lot of light, uses a lens to focus it down into a more concentrated image, if you want to say that, so that we can detect faint objects that we wouldn't normally be able to see if we didn't have the lens collecting the light. The two main problems with early refractor telescopes, and that is that these glass lenses don't necessarily focus light into a sharp point in a couple of different ways. One, different parts of the lens are going to bend light differently, and so things are not going to be sharply focused. That's called spherical aberration. But what was more of a problem is that red light and blue light get bent more at different angles when they go through the glass. So the blue light that's coming from an object is going to be focused at one point, and the red light's going to be focused at a different focal length, and you can't get all those colors to come in. So when you're looking at an object through the lens here, and if there's bad chromatic aberration, then you're going to see things in the telescope, but it's going to have all these rainbows of colors around because different colors are being focused at different depths. That's why people switched over to reflector telescopes, where there's a mirror rather than a lens. That's a parabolic shaped mirror that is meant to take a wide sample of light, bounce it down on the mirror, and point all that light up to a point where it can be focused. Newtonian telescopes are of this kind, reflector basically. And for a century or so, reflectors were the main types of telescopes used to look for Mars. When people came up with the innovation that, well, I can use two different lenses with different glasses that bend red and blue light differently. If I match them up just right, I can get the red light and the blue light to come to a focus at a sharp point, and I can get rid of that chromatic aberration. And so that's why during late 18th and 19th centuries, much of the work looking at Mars was back again on those refractor telescopes. Since we're running behind, I don't think I'm going to spend a lot of time on this, but just realize that light Earth-based telescope work does have a fundamental limit based on the wave properties of light. And that's dealing with this diffraction issue. If you've had any kind of physics, you may remember that light is able to act as both particles and as waves. And light waves coming through any aperture like a telescope, based on the wavelength of the light and the size of the aperture, these wave forms of light set up interference patterns, and you get these diffraction patterns that lead to fuzzy rings. You might have a star or a planet that you're looking at in the telescope, and instead of just seeing that star as a point of light, you get all these bands of other light and dark around it, which makes it difficult. And that is basically a fundamental principle of light. So there are certain limitations. You can't build the perfect telescope that will allow you to, from the Earth, look at tiny, tiny features on Mars. Okay, so why do we locate telescopes up on the top of mountains anymore? Why do we put telescopes out in space like the Hubble Space Telescope? We can build a whole lot bigger telescope on the Earth than the Hubble telescope up in space. What problem do all Earth-based telescopes have to deal with when they are looking at objects in the heavens? The atmosphere of the Earth. Okay. Earth's atmosphere is going to cause the light that's coming in to wave and fluctuate, and the higher you can get your telescope, the more of the atmosphere that you are above. That does a couple of things. With the thinner atmosphere, you don't have as much problem with the atmosphere causing your planets to twinkle or your stars to twinkle. And oftentimes things like clouds and other weather events are typically a lower altitude thing. And if you get, if you're in Hawaii and you're down on the coast, you may have, afternoon thunderstorms rolling in. You go up to Mauna Kea or other places where they've got the telescopes on these high mountains in Hawaii, and you hardly ever see any clouds. So, actually, most people got this question right, that some of the early observations during the geographic period of Mars exploration, these observations made by Beer and Midler, showed that the south polar cap is a lot more variable. It grows bigger in the southern winter and shrinks more in the southern summer compared to the northern polar cap. And the reason for that, we will actually defer to when we talk about climate. Basically, what we talked about in terms of Kepler's laws about how Mars's orbit is elliptical and how Mars speeds up and slows down at different parts of its orbit. Just a quick review. There's aphelion, which is what? Mars is farther, or any planet is when it's furthest away from the sun. Perihelion, closest to the sun in an orbit. So Earth has an orbit around the sun. It's got a point where it's farthest away from the sun, closest to the sun. Mars has same thing, point in its orbit where it's farther away from the sun or closer to the sun. At what part of its orbit, aphelion or perihelion, is Mars booking along the fastest? Aphelion. Show of hands. Mars fastest at aphelion. If that's gonna be your position, raise your hand up and be proud about it. Perihelion. Okay, it's perihelion. Sorry.
No, it's all right.
Again, you might want to think about it as basically as the planet is swinging around closest to the sun. That's when it gets whipped around by the gravitational pull of the sun. And the planets always move fastest at perihelion. And that's going to have influence on what the quality of winter and summer seasons are like in the northern hemisphere versus the southern hemisphere of Mars. And we'll get back to that. Okay. A lot of people had a problem with this question because I think autocorrect screwed me over. The question is supposed to be assuming that the dark area seen on Mars during the period of telescopic observations represented bodies of water. What conclusions did the observers draw about Mars? Based on, I see dark spots, I do see light areas, I think the dark spots are water, I think the light spots are land. What people surmised from that, who were looking at Mars, was that Mars generally must be drier than the Earth. Even assuming that the dark spots that we're looking at were oceans, which we now know they weren't, if you just tallied those up and compared that to the amount of oceans on the Earth, then even with that water favorable impression of Mars, Mars is going to be a lot drier than the Earth. And that feeds into the argument about how Mars ages over time in Chapter 4 and how that influences what's going on with the canals and advanced life. Okay, these waves of darkening, basically Lowell thought, as well as other people, that these were an attempt, either natural in the case of many observers, or artificially in the case of Lowell, that we had water melting at the poles during the spring and summer seasons, and that water eventually moved its way from the polar regions down to toward the equatorial regions. Okay, so as I said, there's tons of dates and events and who did what when in those chapters. I think you can kind of break that all down into three main periods of Mars exploration that occurred before the space age. There's what you might call the astronomical era. This is when Mars went from being a point of light in the sky to being understood as a planet, so a world that was going around the sun. So point of light to planet, world, and who are the important names for this? Major change in our worldview. Whose names do you need to be aware of?
It's not Beard and other, is it?
What?
Beard and...
No, this is way before them.
Like the guy with an S, like really long name.
Schiaparelli? No, way before him too. Okay. So you're stuck in the geographical, let's map the geography of Mars kind of era. Not Darwin directly, but that same kind of, or actually earlier time frame than that is even. Copernican revolution. Who's involved in the Copernican revolution? Copernicus? But who else? Copernicus, Kepler, the big G guy, Galileo. Tycho Brahe, even though he was not a Copernican, without his data, Kepler could not have done the work that Kepler did. And the system that was overthrown was the Ptolemaic geocentric system, but Ptolemy did a yeoman's work of pulling together all that was known about how the geocentric models of the universe worked, and was the authoritative figure. So we're talking about here basically antiquities through about the 16th century. Okay. Fundamental change in our worldview. Earth not at the center of the solar system, but the sun is. Then there's a period where we know Mars is a planet. Let's start getting some of the basic features of that planet. So, axial tilt. What's its seasons like? Day length, polar caps, etc. Who are the names that are really critical for getting us our first understanding that Mars is maybe kind of Earth-like? No takers? Who you should be thinking about is Huygens and Cassini, who worked about the same time. And then a little less than a century later, Herschel. And we're talking really basically the 17th and 18th centuries. So this sets us up for this idea of plurality of worlds, that, if there are other planets, and some of them actually might be Earth-like, then we can start thinking about, is there life on other planets? Is there civilized life on other planets, whether they're humans or not? So then there's this period where we are trying to map the geography of Mars. And here we have names like Beer and Medler. Features actually are constant. There's a big debate about whether what people were looking at Mars in the telescope were those just patterns of clouds, or were they actually being able to see surface features. The observations, extended observations of Beer and Medler, really focused in on that. Their work on the polar caps, showing that the southern polar cap was more variable than the northern polar cap. Started fleshing out our notion about what Mars is like as a world. Dawes and Proctor kind of related. Dawes in particular drew observations of Mars that took into account different color variations. Proctor, in turn, created a fairly famous map of Mars based on the observations of Dawes and other investigators before. By the time you can start creating maps, then you can actually start talking about places on this world. Just as Europeans were busily mapping the Earth, mapping out the continents, the rivers, mountain ranges, and so forth, where civilizations were on Earth. It's pretty much the same thing was going on in the observations of Mars at the time. Okay. A.S.F. Hall. What's his claim to fame? The moons. Phobos and Deimos. And he did some other things, but that's really what he's most known for. By discovering those moons and tracking their orbits around Mars, he could confirm that those moons were traveling in Keplerian kind of orbits around Mars. And from that, he could actually determine the mass of Mars, the mass of the moons, their gravitational attraction. If you have moons orbiting a planet and you can track those moons, you can actually weigh the planet, which is kind of cool. Flammarion we'll forget about. Pickering we'll forget about. Schiaparelli. What's his main contribution?
Is he the one who found the dark blue band?
Yeah, but well, not found. He's Italian, and what term, very fateful term, did he apply to features on Mars? Canali, which in Italian means either channel or canal. Lowell, of course, turned those into canals, and the rest is history. We'll talk a lot more about Lowell, and I think I will cut it off there. I do have on the other slides some of the example maps from the different eras, but I'll just post those.